Is a molecule a polar molecule or a nonpolar molecule? By the end of this video, you'll know how to analyze a molecule and determine whether it's polar or nonpolar. Very briefly, why does it matter if a molecule is polar or nonpolar? It matters because the properties of molecules, for example, their state of matter at room temperature, depends very much on whether the molecule is polar or nonpolar. Take water, for example. It's a liquid, whereas carbon dioxide, what we exhale, is a gas. Why is carbon dioxide a gas at room temperature, whereas water is a liquid? Well, it has something to do with polarity, and we'll talk more about that in our next video on intermolecular forces. So let's go over the steps for determining whether a molecule is polar or not. Step one, you've got to draw the Lewis dot diagram. This will help us determine the structure of the molecule and what bonds are located in the molecule. Step two, determine if there are polar bonds in the molecule. We have to draw polarity arrows. That's going to be very important for step three. And if there are polar bonds, then we have to analyze. Do the polar bonds cancel out? What we're looking for really is, do the arrows cancel out? If all of the arrows cancel out, we're left with a nonpolar molecule. But if some of the arrows don't cancel out, it's going to be a polar molecule. All right, so let's do some analyses from our molecule polarity notes and the molecule polarity worksheet. So let's pull that over. And CCl4, which was example 3 on the molecule polarity worksheet. Okay, so step one is to draw the Lewis dot diagram for CCl4. If we look at the periodic table, we'll see that carbon is in group 14, so it's got 4 valence electrons, and Cl chlorine is in group 17, it's got 7 valence electrons. So let's get rid of our periodic table here and get drawing our molecule. So carbon's written first, it's going to be the central atom. 1, 2, 3, 4 valence electrons. We're going to have 4 chlorines, and they'll be located at the 4 bonding sites for carbon. 1, 2, 3, 4, 5, 6, 7. Note that there's a free electron on chlorine and 1 on carbon. They'll be able to share and bond. We'll have 3 more chlorines that will bond around the carbon. I'll assume that we're good on Lewis dot diagram drawing, so I'll just jump to our final product here. Cl, don't forget your lone pairs. And lone pairs over here as well. Okay, so we've done step one, which is draw the Lewis dot diagram. Now let's determine if there are polar bonds and draw polarity arrows. So again, let's bring out our periodic table. Here's carbon, here's chlorine. Remember, the most electronegative atom is fluorine. Chlorine is pretty close to fluorine, so it's going to be quite electronegative. Carbon is a distance away from fluorine. It's going to be less electronegative than chlorine. So therefore, if chlorine is more electronegative than carbon, it's going to pull harder on the electrons in the bond, and it's going to be pulling electrons closer to itself. It's going to be the more negative atom. So let's diagram this with polarity arrows. Going to be an arrow this way, an arrow this way, an arrow this way, and an arrow this way. Notice, we're going to diagram each of these carbon-chlorine bonds with polarity arrows. And the analysis for each bond is going to be identical because they're both carbon and chlorine bonds, or at least they're all carbon and chlorine bonds. So now let's take a look at step 3. Do the polar bonds cancel out? Because if they do cancel out, we're going to end up with a nonpolar molecule. If they don't cancel out, it's going to be a polar molecule. So let's take a look at these two here. They're opposites, pulling exactly apart. These are going to cancel out. And these are also going to cancel out. So what we have here are polar bonds but a non-polar molecule. All of these bonds cancel out. So therefore, we have a non-polar molecule overall. Okay, let's go on to our next example, which is H2O water. Again, first step is to draw the Lewis dot diagram. Let me pull that down. And we're going to have an oxygen. Oxygen has 6 valence electrons, group 16. Hydrogen, of course, is in group 1, 1 valence electron. So oxygen, 1, 2, 3, 4, 5, 6. And we're going to have 2 bonding sites on the left and on the bottom. So a hydrogen here and a hydrogen here. They'll be able to bond like that. So H2O will look like this. Don't forget your lone pairs on oxygen. Step 2, determine if there are any polar bonds. Let's bring our periodic table back out here. Well, we've got oxygen, very electronegative. It's all the way in the upper right of the periodic table, right next to fluorine. And hydrogen is not very electronegative. Still a nonmetal, but it's for a nonmetal, it has the least electronegativity. So this is going to be a very polar bond for nonmetals, for covalent bonds. So oxygen is more to the right of hydrogen, so the electrons are going to get pulled towards it. So we'll diagram our polarity arrow with the electrons getting pulled towards oxygen. Now, step 3. Do these bonds cancel out? Well, they don't. One is getting pulled up, one is getting pulled to the right. They're not exact opposites of one another. So overall, there will be a polar pull like this in the molecule. The oxygen is going to be more negative, and back here on the hydrogens, they're going to be more positive. Partial negative on the oxygen, partial negative, and partial positive back here by these hydrogens. So this is a molecule with polar bonds, and the molecule overall is polar. Polar molecule. So let's do our third compound now. This is an example from the polarity worksheet, CH4. That would be carbon tetrahydride. So let's again do step 1, which is draw the Lewis dot diagram. Looking on our periodic table, carbon is in group 14, so 4 valence electrons. Hydrogen group 1, 1 valence electron. So carbon, 1, 2, 3, 4, and we'll have 4 hydrogens around the carbon. I won't draw all 4 of them. I'll just draw this one here just to show that we'll get a bond like that. Well, why not? Let's draw all 4 of these hydrogens. All right, 1, 2, 3, 4 bonds. 1, 2, 3, 4. H, 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 H. Carbon tetrahydride. Okay, now let's go to step 2. Determine if there are polar bonds, and if so, draw polarity arrows. Let's go back to our periodic table. So carbon's here, hydrogen's here. You may think that the carbon-hydrogen bond is polar because they're quite a distance away from each other on the periodic table. But the carbon-hydrogen bond is a nonpolar bond. The difference in electronegativity between carbon and hydrogen is actually really low, because carbon is actually not particularly electronegative for a nonmetal, and neither is hydrogen. So we're going to end up with a nonpolar bond for carbon and hydrogen. How do we diagram a nonpolar bond? Do we use an arrow? No. We just can say this is a nonpolar bonds, because the carbon-hydrogen bond is nonpolar. It will always be nonpolar. Now, let's go to step 3. Do the bonds cancel out? Well, we don't have any polar bonds, so there's nothing to cancel out here. And if you have only nonpolar bonds, we don't have any partial negatives or partial positives in this molecule here. If you only have nonpolar bonds, you will always end up with a nonpolar molecule. Let me write that. If you only have nonpolar bonds, the molecule will always be, let me move this up, nonpolar. So, and actually let me move it up even more. There we go. So, CH4, only nonpolar bonds, because we only have carbon-hydrogen bonds. So this molecule is going to be a nonpolar molecule.